In today's video, we are going to learn about arc and angle measures inside circles. Just waiting for this all to animate. Okay, so let's review what we learned last week, which is the difference between a central angle and an inscribed angle. So starting with the central angle, we have the center of our circle here. Let's call that a point C. And let's say we have an angle starting at the center of our circle that intersects our circle circumference at points A and B. So the measure of this angle, let's say it's 85 degrees. If you wanted to find the measure of the arc that is intercepted by angle C, this arc right here, that arc has the same measure of the angle, which is also 85 degrees. So central angles and their arcs have the same measure. In this case, angle ACB measures 85 degrees and arc AB measures 85 degrees. Central angles have the same measure as their intercepted arc. Now let's take a look at the inscribed angle. So if we have this same situation, but let's say you have another point along your circle's circumference, say point D, and then we connect that point to A and B. We have another angle here, ADB. So the measure of this angle is always going to be half of the intercepted arc. So since arc AB is 85 degrees, arc angle ADB is 42.5 degrees because it's half of the intercepted arc. So now we're going to learn about the three cases of where your intersection of some secant lines can be and how to find angle measures based on those. So we could have an intersection inside the circle, outside the circle, or on the circle. So the first case inside the circle would be when you have two secant lines that intersect at a point that's inside the circle but is not the center. Another case could be that you have two secant lines, or maybe a secant and a tangent, that intersect outside the circle. The third case we've actually already looked at, which is the case where the intersection is on the circle. This would just be the case of an inscribed angle. So just like the one that we just looked at. So lines can intersect in these three places only, inside, outside, or on, and based on the cases, I have a little arc there. So inscribed angles, we already know about. The arc measure for the inscribed angle is going to be twice as much as the angle, or the angle is half of the intercepted arc. So for the on the circle case, we already know that. The two cases we still need to look at are what happens if you have an intersection in the circle that's not at the center, so it's not a central angle, or an intersection outside. So you should have a capture sheet that you got as a link from your teacher. If not, I've linked it in the description box below. So please open up that capture sheet and follow along as I go through these examples. So here is the first case of a intersection that is inside your circle and it's not at the center. So you'll notice that we have two vertical angles here, and we can call those N. So each of those angles measures N degrees. We don't know what it is, but they're the same since they're vertical angles. We also have two intercepted arcs from these angles. So we have this first arc here and this second arc here. We'll call this one X and this one Y. So the two angles, the two vertical angles, intercept two arcs X and Y. And to find the value of the angle N, the relationship that we have here is that 2N, so those two angles together, is equal to X plus Y. So the sum of those vertical angles is the same as the sum of the arcs that it is cutting off. Another way of thinking about this is that one angle, N, is equal to X plus Y divided by 2. So if you wanted to put that into terms to help you remember, you could say that the measure of one of the vertical angles is the average of the intercepted arcs. So if I want to know the measure of angle N, I can add X and Y and divide by 2. Now, this isn't the only way that we could look at this. If we take all of that marking off, we could have actually gone the opposite direction and thought about these two vertical angles instead. So what if these were what we were thinking about with angle N? Well, the relationship is actually still the same. You have this big intercepted arc at the bottom and a smaller one at the top. You still think about those arcs in terms of X and Y, and the vertical angles in the middle in terms of N. The relationship is the same, so 2n equals x plus y. N is x plus y divided by 2, or the measure of one of the vertical angles is still the average of the intercepted arcs. So no matter which way you go with it, it's going to have the same value. Okay, so that's inside the circle, but what if our intersection is outside the circle? In that case, this diagram has pretty small angles, so I'm going to try to label them as best as I can. So we have one vertical angle here at n, and another vertical angle here at n as well. So both of those angles measure n degrees, and sometimes you won't even have like the backside like coming off of the end there. It might just like make an angle and stop, like the second one that came up there. That was a poor explanation, but you'll see in one of the examples that we did, you don't always have to have the vertical angles when you have an intersection outside the circle. Sometimes it just kind of looks like a triangle. So we have two intercepted arcs again. So the first one over here we'll call x, and the second one we'll call y. So x is this larger intercepted arc, and y is the smaller one. And it is pretty important that you think about x as being the larger one and y being the smaller one. To find the value of n, here are two ways to think about it. First, 2n, the two angles together, is equal to x minus y. Notice the difference between last slide and this slide is that we're subtracting now. The other way to think about this is that one of the angles, n, can be found by doing x minus y divided by 2. So if it helps for you to see that in words, to calculate the measure of one of the vertical angles, subtract the smaller arc from the larger arc and divide by 2. So now that we have seen outside and inside the circle, we now have this framework of inside, outside, on, if you put that with the inscribed angles that we've learned about before, and we can move on to a graphic organizer that's on your capture sheet, and it looks like this. So you're going to go to your capture sheet and you're going to fill in the equations for each case. So the first case is your lines intersecting inside the circle. We saw that n, the value of one of our interior angles, should it be called interior? I mean, it's inside the circle. So one of our angles is x plus y divided by 2. So you add the intercepted arcs and divide by 2. If you are having trouble typing this in your Google Doc, one option is to go to Insert Equation, and you can use the equation editor to make it look nice like this. That's how I made these nice fractions. Otherwise, you can just type it in a way that makes sense to you. The second case is if secant lines intersect on the circle. So that's just an inscribed angle, and the value of n is equal to the arc divided by 2, because you only have one intercepted arc. In the third case, for secant lines outside the circle, our summary here is that the value of n is x minus y divided by 2. So you can pause the video here and make sure that you have all of this typed into your capture sheet, and then we're going to do 3 example problems together. So here is our first example. It's really straightforward. We need to find the value of x, and the first thing you want to do is determine whether you are dealing with an intersection that is inside, outside, or on your circle. So this point right here, the point of intersection for our secants, I mean, these are really just chords because they don't extend beyond the circle, but either way, it's the same process. This intersection is inside the circle, not at the center. If it was the center, it would just be a central angle, and that would be easy, but this is not a central angle. So we pick our formula accordingly, which is that you add x plus y and divide by 2. So 120 plus 40, those are our arcs divided by 2, so that's 160 divided by 2, and the measure of angle x is 80 degrees, or the value of x is 80. Pretty simple, right? Pause the video here if you need to fill in your capture sheet. Next, we have an example that looks like this. And the point of intersection, this is what I was trying to describe a few slides ago. See how the point of intersection doesn't have vertical angles, it just kind of stops? That's okay, it's the same process. So this point here is outside of our circle, and we want to pick our formula accordingly. So the formula we're going to use is x minus y divided by 2. So we do 82 minus 26, it's important that it's the larger one minus the smaller one, divided by 2, which is 56 divided by 2, so the value of x is 28, or x, that angle measures 28 degrees. All right, we have one more example. So in this case, instead of having a missing angle, we have a missing arc. So what we're going to do is use our formula, and we are going to find what we know, plug it in, and solve for what we don't know. So in this case, we can see that the intersection is inside the circle and not at the center. If you're ever having trouble figuring out if it's the center, basically they will tell you if it is the center, and if they don't tell you it's the center, you have to assume it's not. So inside the circle, not the center, which means we're using this formula again, x plus y divided by 2. So if I multiply by 2 on both sides, so 2n equals x plus y. So x, I'm just going to leave as x, and for y, I'm going to use 55. So 2 times 60, which is n, is going to be 55 plus x. So on the right-hand side there, I have 120 equals 55 plus x, and then you can just subtract 55. So basically what you do is you double the angle in the middle and then subtract one of the arcs. Pretty simple. So the value of x is 65. All right, so that was our final example. As always, you can run back through the video, you can change the speed that it's playing at, you can look through some more examples, pause if you need to, but this concludes our study of arc and angle measures in circles. Thank you.